this is Dr. Muhammad, and this is a new video under engineering mathematics. Today we are going to talk about matrices. This is the first video regarding this topic. So I'm going to indulge into the topic directly with the introduction. And today actually I'm going to talk about an introduction of for matrices. So it is going to be something, I think it is going to be something easy for most of you, because I think that you have an idea about matrices or about working with matrices. Today I'm going to give some definitions and introduction for it. Okay. Now let's go to directly to the definition part of the matrices to know more about it. Now, what is the meaning of matrices? Matrices are considered to be like a form by which that we are going to put some set of numbers. So we're going to use like specific form, and we are going to fill this specific form with numbers. Okay, so that's the main idea of the matrix, because in many applications we need to use a numerous numbers or different numbers, and there is no way or there is no procedure to express these set of numbers or this set of numbers in an appropriate way similar to matrices. So again, it is only like arranging the numbers in a form that is easy to be handled, easy to be manipulated, and easy to use it in different applications. So let's assume that we have an n by m or n times m matrix is a rectangular array of objects arranged in n rows. That's the meaning of n here. It means that n rows, as we are going to see now, and m columns. We will denote matrices in boldface. In general, we're going to say that if we have a matrix, this matrix is going to have a name. This is the name, for example, and we are going to use a boldface for representing the matrix itself, which is A or B, for example. So boldface, it is not, you are going to find it bold. So whenever I write, for example, A dot B, from now on you should understand that A does not mean a number, it means a matrix, especially if it's bold. Okay, if it's bold like this, so this means that it is a matrix, and B also is a matrix. Okay, so the multiplication or addition or whatever the operation that we are going to apply, it doesn't work as if that you are adding or multiplying numbers. Okay, it is different. Okay, and whenever we say n and m, this means that we are having n, this is the number of rows, this is number of rows, and m is the number of columns. Okay, so this is why we said that n, it is the rows, and m, it is the columns. So the rows, as you can see here, for example, this is A. We put it between parentheses like this, and this is the row, the first row here. As you can see, we have 1, 2 rows. So we put it, we denote it like here. This is 2 rows by, these are the number of columns, 1, 2, 3. So we have 3 columns. In each row, there is like set of numbers are provided, as you can see, 2, 1, and pi. Here it is 1, radical 2 minus 5. So they are like, as I said, set of numbers are arranged in each row, and also if you are going to take it from the column point of view, that each column has a set of numbers. Okay. Now this matrix, as we said, we can say this matrix is A 2 by 3. Okay, so is a matrix 2 by 3 matrix. This signifies that we have 2 rows and we have 3 columns. In a similar fashion, if we have B As you can see here, we have 2 rows, so it is 2 by 1, 2, 3, 4. So we have 4 columns, so it is 2 by 4. So B in this case, it is 2 by 4. Okay, and this B, we call it a matrix or 2 by 4 matrix. Okay, so this is the definition of the shape of the function, the shape of the matrix itself, and the meaning of the rectangular array. Okay, so a matrix is arranged or is a rectangular array of objects arranged in n rows and m columns. Okay. So let's go and see what are the second definition for this important for us. If we have 2 matrices A, and we are going to denote A as, or we are going to put A in this form, A between brackets, a small letter A, and then here we're going to find I and J. So this means that the element that is going to be in row I and column J, okay, between the parentheses. Commonly, and whenever that we use B, for example, we use the same, the lowercase b. So this is whenever we have uppercase, this means the matrix. When we use the lowercase, this means the element of the matrix itself. And then the subscript is going to be I and J. So I, this means that the row, and whenever we use J, this means that the column. Okay, so we have row and the column. For this, and we put it between parentheses. Okay, so I and J, this means that element, it can be number. Okay, it is 2 or 3 or 4 or 5, anything. But A, capital and boldface, this means that it's a matrix. Okay, take care of this. So 2 matrices A and B are equal if they have the same number of rows and the same number of columns, and for each I, which is each column, and J, each I, each row, and each J, which is the column, AI equal to AIJ, so it is AIJ element in row I and in J column in the matrix A should equal to the element in row I and the same column J in the matrix B. Okay, so that's the meaning of whenever we say that we have A equals to B, this means that a set of things. If they have the same number of rows, so we need to have the same number of rows. So if this is A, for example, so we have like 1, 2, 3. So this means that it must equal also 1, 2, 3. We have 3 rows here. Okay. So if it's like 3 by 2, then this one should be 3 by 2. We have 3 columns here. This means that we are going to have like 2 columns here, and we must have 2 columns here. Okay. Each node here is considered to be the element. Okay. So that's the meaning of the equality between 2 matrices. Okay, and we say that Aij must equal to Bij. What is the meaning of this? The column itself, or the element, sorry, itself, this element, if it's 4, this means that this element here must be 4 also. Okay, so that's the mean of equality of matrices. Equal matrices have the same dimensions. So we understand now what is the meaning of dimensions, okay, which is, as we said, it is like 3 by 2. And objects located in the same positions in the matrices must be equal. So they are having the same dimensions, and objects, we call them the objects or elements, okay, located in the same positions, and the matrices must be equal. So the element themselves should be equal as well. Okay. So this is regarding regarding the equality of matrices A and B. Okay, now let's go to something else which is related to the matrices operations. Operations here means that like multiplication, addition, and something like this. We want to understand more about them. There are three main operations. Okay, we will define for matrices. So we're going to talk about three main operations actually for us. Addition, we're going to talk about addition, how to add two matrices together. Multiplication by a real number, if we have a matrix and we are going to multiply by a real number, how we are going to do so. And multiplication. Okay, so we're going to, multiplication means that two matrices multiplication together. Okay, so let's start with the addition of matrices. If we have matrix A, which is, as we said, denoted as parentheses Aij, these are the elements inside this matrix A, and we have Bij, which is another matrix, are both n by m matrices. Take care, both, they are n by m. This means that they are having n and m matrices. Number of rows n, number of columns m, both of them. Then their sum is defined to be the n by m matrix A plus B, which is the element of matrix A at the row I and column J plus the element in matrix B at the same row I and the same column J. Okay, so that's the meaning of the addition of matrices. We add two matrices of the same dimensions by adding objects in the same locations in the matrices. For example, if we have, this is matrix A, let's assume that this is matrix B here, and these are the elements of matrix A, and these are the elements of matrix B. So when we are adding them, we are going to add this element with this element, A minus 1, so it is going to be 0 here. Then 2 plus 6, it is 8. And then minus 3 plus 3, it is 0. And so on. Also 4, 8, it is going to be 12. 0 and 12, it is 12. 2 plus 14, it is 16. So that's this means that we are adding up the two matrices together. We are adding up the two matrices together. We can think of this as adding respective row vectors or respective column vectors of the matrix. Actually, each matrix is considered to be having like set of vectors. So if we can say this matrix is having 3 vectors, okay, as columns, or 2 vectors as rows. Similar here for B, it is going to have 3 vector columns, column vectors, and or we can say or it is 2 row vectors. Okay, this row and this row. Okay, so that's the meaning. What I want you to know about this, that addition of the matrices means that addition of their elements together. The elements inside the matrices are going to be added together. Okay, one thing that you should understand is what? This word. Both are having what? N and M. So this means that if you have a matrix, like, let's assume it is 2 by 3, okay, and you want to add another matrix, which is, for example, 3 by 3. Then, how we are going to add them? The answer is no. They are not going to be added. Why? Because they are not having the same dimensions. Okay, so that's important. Here we have 2 rows, here we have 3 rows. So this wouldn't work for us. So remember, this is considered to be keyword here in addition of matrices, which is both are having the same dimensions exactly. Okay, so this is regarding the addition of matrices. Let's go to another thing, which is the multiplication by a scalar. A multiplication by a scalar. Okay. Multiply a matrix by a scalar quantity, say a number or function. So it can be like scalar number or maybe function, by multiplying each matrix element by the scalar. So each element of this matrix is going to be multiplied by the scalar. If A equals to Aij, which is the elements of the matrix A, then C, which is small c here, this means that scalar quantity, okay, times A equals to, this C is going to be multiplied by each element inside the matrix. For example, if we have, this is the matrix here, this matrix is 1, 2, 3, 4. It is 4 by 1. This is the dimension of this matrix, which is a vector actually here. If we're going to multiply it by the radical square root of 2, then each element here is going to be multiplied by the same scalar quantity. So we're going to have here in the first element minus 3 radical 2, 4 radical 2, 2t, even that it's a function here, square root of 2, and then sine 2t. It is the same, multiplied by the same scalar value. Is multiplied by the same scalar value. Okay, this is the same as multiplying each row vector or each column vector by C. This is the same as we said. It is as if that we have multiple rows, okay, multiple rows or multiple columns, and we multiplying by a scalar function or quantity in general. Here it is a function, and we have here our dimension is 1, 2, 1, 2. So we have 2 by 2 matrix, okay? Then we are going to multiply this cosine in each of the elements of this matrix. So here is 2 times cosine t. It is going to be 2 cosine t. Here e to the power t, it is e to the power t cosine t, and then sine cosine, this is cosine sine here, and this is 4 cosine t, which is 4 cosine t. So this means that we are, whenever that we multiply a scalar quantity by our matrix, it equals to that multiplication of this scalar quantity by each element inside the matrix itself. Okay, this is important for us to realize. Okay, now let's go to the next part, which is multiplication of matrices. So this is the third type of operation that we are doing. Okay, so now let A equals to Aij be n by k. Take care of the dimensions here. N by k. So we have n rows, k columns. And B, which is the matrix of the elements of B, Bij, be k by m. Take care of the dimensions. Okay? So we have A n by k. However, we have B, it is k by m. Okay. Then the product AB, this is the like the way that we express the multiplication of two matrices. It is A times B. Without anything, without putting anything here. It is similar to as if that we are putting it for the elements. Okay, but remember that they are matrices, not elements. Is the NM matrix. It is NM matrix. Wow. So here we said that we have n by k, and we have B to be k by m, but whenever that we have the output or the product AB is going to be something else. It is not going to be the dimension of one of them. It is going to be n by m. Here it is the number of rows of the first matrix, and here it is the number of columns of the second matrix, right? So if we have, for example, A 2 by 3 times B, which is, let's assume it is this is 2 by 3, so let's assume that this is like 3 by 4, for example. So take care, this can be multiplied or not. The answer is yes, because we have here, this is nk, this is n by k, and here this should be, the b should be k by m, k, which is the same number of columns in A equal to the same number of rows in B. Then our AB, which is AB, this is the AB, is going to be exactly 2 by 4. 2 by 4. Okay, understand? This is an important issue. Then the product AB is then n by m matrix whose I and j elements as, this is the elements of I and j. We are going to see the example here, which is A I1 times B1j. So we're talking here I1 times B1j. Okay, so this means that we are as if I, it is the row of the element and the matrix A. B1, it is row 1, J, which is J column in the second matrix, and so on and so forth. So we are going to see that this is going to be given as, I'm going to give you the example instead of understanding this. Maybe it's a little bit like difficult to understand this, but the example would be easier to understand. Okay, I'm going to show to you what is the meaning of the summation of the the product of the elements, how we can do it. Okay, so this is the dot product of row I of A. This is actually, as you have taken it before, studied before, it is the dot product of row I of A with the column J of B. Both are vectors. Okay, so I and J elements of AB, it equals row I of A dot product of column J of B. I'm going to show you an example, but before going to the example, I want to highlight something here, which is this note that I put it here. So first of all, we need to understand that the number of rows here in the first matrix is going to be the number of rows in the output product, and the number of columns in the second matrix is going to be the same number of columns in the output product. So we have these, needs to be taken into consideration. Another point is that K, the number of columns in the first element in the first matrix should equal to the number of rows in the second matrix. This is a must to make the product. Okay, let's go outside of this and have an example to understand what we are talking about. Okay, let's have A, which is, as you can see here, it is 2 by 2, right? And here B, which is 1, 2, we have 2 rows times 3 columns. So we have 3 here. First of all, we need to check whether they can be multiplied or not. The point is 2, it is the number of rows here, and we have the number, the number of columns here, which is K, as we said, this is 2, and the number of rows here is 2. So this means that the multiplication can work now. Okay, it can work. Okay, now our output product, the product, which is going to be A by B. So we have here A, which is 2 by 2, okay, and we have dot B, which is 2 by 3. The output product is going to be AB. We checked that the number of columns here in the first matrix equal to the number of rows in the second matrix, so we can find the product of this multiplication. And the product is going to be exactly, we're going to take this row number in the first matrix and the column number in the second matrix. So we are going to have our multiplication product is going to be 2 by 3. 2 by 3. So let's have this and see. Here A is 2 by 2 and B is 2 by 3, as we have seen. So we can compute AB, which is 2 by 3, as I said to you, as we have explained. Number of rows of A and number of columns of B. That's what we have. Number of rows of A, number of columns of B. In terms of dot products of rows with columns, so AB is going to be like this, putting the two matrices together, 1, 2, 3, 5 here, and the other matrix, which is B. So it is going to be the multiplication is going to be like this. Number of rows of A and number of columns of B, right? So we're going to look to the first row here. It is going to be 1 and 3. So we say that this is like this vector, which is containing 1 and 3. We are going to dot product with 1 and 2 here, which is the first column. So this is the first column in the second matrix B. And then the second element, so this is the first element in the output product, which is AB. The second element in the same row is going to be 1 and 3 vector, which is the row, times the second column in the second matrix B, which is 1 and 1 here. So this is the second term in the matrix multiplication AB. And the third element is going to be 1 and 3 vector, okay, times the column here, which is 3 and 4. 3 and 4. So we have the vector row and the vector column here. So this is the first row of the multiplication. Okay. So if you are going to, and the second row is going to be taking the second row of this matrix A, which is 2 and 5, 2 and 5. This is the vector 2 and 5, dot the vector 1 and 2, which is 1 and 2 here. Okay, and then 2 and 5, the same row vector times the row the column vector, which is 1 and 1, and here it is going to be 2 and 5 dot 3 and 4, which is, as you can see here. So it's very easy for us now. We can get the first element of the matrix, which is, this is going to be 1. So the first element is going to be 1 times 1 plus 3 times 2. This is 1 times 1 plus 3 times 2. So it gives us 7, which is this element. Okay? The second element is going to be 1 times 1 plus 3 times 1. So it's going to be exactly 4. And the fourth element is going to be 1 times 3 plus 3 times 4. So it gives us 15. And here 2 times 1 plus 5 times 10. It is 12. Similar here, it is 2 times 1 plus 5 times 1. It gives us 7. Here 2 times 3 and 5 times 4. It gives us 26. Okay, so look to the output here. It is what? Exactly 2 by 3 matrix. 2 rows and 3 columns. 2 rows and 3 columns. Okay, in this example, BA, so this is the AB now, right? Okay, so it works for us. AB works for us. Okay, I think that using this example, you can give and make multiplication for any two matrices. Remember well that the dimensions matter. The dimension of the matrices matters, and you have to check that the number of rows here, sorry, the number of columns in the first matrix equal to the number of rows in the second matrix. Okay, so now AB, it works for us and we could obtain it. But what do you think if I ask you, please get B times A? Is it going to work for us? Actually, let's see. We have here B, as we said, it is 2 by 3. So if we are going to say B, which is 2 by 3, dot A, which is 2 by 2. Then their product, the first trick is what? Exactly. The column here, the column in the first matrix should equal to the rows in the second matrix, which is not equal in this case. This means that BA does not exist. It will not be there. So in this example, BA is not defined. It is not defined because the number of columns of B does not equal to the number of rows of A. Okay? So that's the point here. So it's not, as we said, as we are going to see, that AB does not equal to BA. It's not like numbers. Okay? It is not like numbers. Remember that well. Okay. Now let's go to the next part, which is another example that we need to know. If we have A, as you can see, it is 2 rows. So we have 2 here times 1, 2, 3, 4. We have 4 here. And B, we have 1, 2, 3, 4, which is 4 rows times 2 columns, as you can see. So we have 4 by 2. Okay? So we are going to first check. We need to check the number of columns in this matrix should equal to the number of rows in this matrix. Okay, so this means that our multiplication works. AB, it is defined because A is 2 by 4 and B is 4 by 2. Then AB is defined and is 2 by 2. So our AB is going to be exactly, we have 2 here, we have 2 here. So our AB is going to be 2 by 2 matrix. Okay, how we're going to do this? We're going to have the first row here, as you can see, 1, 1, 2, 1, and we're going to multiply it by the first column here, which is minus 1, 2, 1, 12. Can we multiply this? If you multiply 1 times minus 1, which is minus 1, and plus 1 times 2, and plus 2 times 1 plus 1 times 12, it would give you 15. If you calculate it, you are going to find that it gives you 15, for example. Similar here, you are going to make the multiplication, which is what? It is we having the same row, the first row of the matrix A times the second column of matrix B. So it is 1, 1, 2, 1, 1, 1, 2, 1 times the column 8, 1, 1, 6, 8, 1, 1, 6. Okay, so this is the case. And what about the second row of this multiplication? It is going to be exactly the second row here, which is 4, 1, 6, 2, 4, 1, 6, 2 times the first column here, which is minus 1, 2, 1, 12, minus 1, 2, 1, and 12. This would give us 28 if you multiply. Okay. As I said, the multiplication, first element times the first element plus the second times the second, third plus times the third, and the fourth times the fourth. This gives you, the summation would give you 15 here, or it would give you 28 here. And also the last one is going to be similar. It is going to be the second row times the second column here, and this would give us 51. You can check it by making the calculation by yourself if you want it. In this example, BA is also defined. Oh, so we are now looking to BA, not AB. If I ask you, please define BA. So we're going to check that first. B is, as we said, B is 4 by 2 times A, which is 2 by 4. In this case, we have the number of columns in B equal to the number of rows in A. So they are equal. This means that our BA is defined and it is going to be 4 by 4 matrix. 4 by 4 matrix, right? So now we can understand that AB is a 2 by 2 matrix. However, BA is exactly 4 by 4 matrix. Totally different. They are totally different. Okay, so how we can get B and A? So this is BA. It is going to be minus all the columns of B are going to be arranged here. And as we said, we're going to have first row here times the first column here. This gives us the first element here. Then the same row is going to be multiplied by the second column, which is going to give us the second element in this row. And the same, this row in the third column, this would give us the third element here. And the same for the fourth, then it would give us the element here. And so on and so forth for the remaining. You can do it by yourself to get sense and to have the practice of doing it. Even when both A and B, AB, which is the product AB, and the product BA are defined, as in our case, these matrices may not equal. Okay, they are not equal. Do you remember what is the meaning of equal? Exactly, that the first matrix should equal in the second matrix if we have the same dimensions, and each element inside the matrix should equal to each element, corresponding element in the second matrix. In our case, AB does not equal BA. Okay, because as you can see, this is AB, totally different in dimensions and elements from BA. Okay, these matrices may not be equal and may not even have the same dimensions. Matrix multiplication is non-commutative. That's the main key word in our multiplication. Multiplication is non-commutative. Non-commutative. Okay, so we cannot say that AB, okay, we cannot say AB equals to BA. We cannot say something like this. Okay. Let's go to the properties of matrix operation. We're going to talk about some properties important for us for matrix operations. Okay. Now, we are going to find that if we have A, B, and C, B matrices, then whenever the indicated operations are defined, then first operation, A plus B equals to B plus A. So matrix addition is what? Exactly, commutative. Okay, take care of this. It is commutative for the addition. Okay. Okay, but for multiplication, not necessarily be the case. Okay, and if we have A times B plus C between parentheses, this means that matrix A times B, AB, plus matrix A plus C. It can be, it works like this. Okay, it works like this. AB plus AC. If we have A plus B times C outside, so A times C plus B times C, A times C plus should be B times C. I think there is some mistake here. This should be B. Okay, so this should be B. A times C plus B times C. Okay, so this is B. And if we have A, B, C, it would equal to, if we have AB, which is the multiplication of A and B, times the matrix C, this would equal to the multiplication of A times the multiplication of BC. Okay, so as we said, it's very important here if we have like the matrix. Okay, this is in the addition, it is okay for us. We understand that everything is going to be added because it's commutative and everything is going to be okay. So if we have B and C, they are going to be added. Okay, they can be added together and multiplied by A. This would give the same answer as A multiplied by B added to A multiplied by C. So this is understood. Here, similar, if A and B are going to be added together first and then multiplied by C, this would equal to A times C plus B times C. Okay? And if we have AB multiplied together already and we want to multiply it by another matrix C, then this would equal to A times the multiplication of B and C. Okay, and if we have any scalar function which is C, A, and B, C times A times B, then it would equal to C times A times B, or it would be the matrix A times C times B for any scalar or for any scalar C. Okay, this is important operations that we need to keep it in our mind. Okay, let's have now the example for this. There is in general no cancellation in the products. So for example, if we have AB equal to AC, so take care here, this is the A matrix here and A matrix here. So you think that we might cancel A and cancel A from here, then B equal to C. This not work. This is not right. So it doesn't follow that B, I think this is a mistake also in the book. So B, okay, it does not follow that B equals to C. So we cannot say that B equal to C. Okay, it doesn't follow, means that B should not equal to C. To illustrate, let's have an example to understand it. So we have like this matrix 1 3 1 3 and another matrix 4 3 2 16. They are okay, 2 by 2 here, 2 by 2. This means that they are available to be multiplied. If you multiply them, okay, we're going to say that we're going to use the same matrix here, 1 1 1 3 3 as the same. This is the matrix A here, and we're going to use another matrix here which is 2 7 5 11, different than this. So this is A, which is the same as A here. This is matrix B, which is different than C here. If you multiply these two matrices, they are going to give you this matrix 7 21 18 54. And if you multiply A and B, it would give you the same answer. Okay, so that's how it goes actually. But you cannot, even that you have A equal to A here, the same matrix exactly, but B does not equal to C. B does not equal to C. That's what we want to say. As you can see, B is totally different than C, even that the multiplication is the same. Okay, so now we put this, that 4 and 2, this is the two matrices are not going to be the same. The product of two non-zero matrices, that's important, may be a zero matrix. It's okay. For example, this non-zero, 1 2 and 0 0, but take care that there is a row of zeros here. This is a key, but later I'm going to talk about this. And the other one is the matrix 6 4 minus 3 and minus 2. If you multiply this, you're going to find that all the elements are going to be 0 in the multiplication. Even that this is not 0 and this is also non-zero, right? I mean that all the elements are not 0, but you found that the multiplication brings 0. It's totally different than the number multiplication, right? Okay. Now let's go to the terminologies and special matrices, so that we have like some special matrices. The zero matrix, it is something very easy and very simple for all of us. So n by m zero matrix, okay, which is, we call it like O, n by m. It is n by n matrix having every element equal to 0. For example, O 2 by 3, it is 2 by 3. This means that all the elements are 0. right? And if A is n by n, then A plus the zero matrix would equal to the zero matrix plus A, because it's commutative. It is commutative, as we said, so no problem here. And they are going to give us at the end the same matrix exactly, which is A. The negative of a matrix A is just a scalar product, which is minus 1 times A. It's the negative of A means that minus 1 times A, formed by multiplying each matrix element by minus 1. It is a scalar function, as we are giving like minus 1 times the matrix A. This is the meaning of minus A. Okay. We denote this matrix as minus A. We call it minus A, as I put it here. FB has the same dimensions as A. Then we denote B plus minus A as B minus A, as we do with numbers. So it is the same. So if we say that B matrix plus the negative of A, this means that, or minus A, this means that B, as if B subtracted from being subtracted by A. Okay, so that's the meaning here. It's pretty simple, I know, and you understand this very well. Now let's go to the next, which is the square matrix and the identity matrix. So the square matrix here is the one having the same number of rows and columns. The same number of rows and columns, they are the same. So the dimension is going to be, like if we have A 3 by 3, for example. Okay, this is the square matrix. And the diagonal, the main diagonal of this matrix consists of matrix elements A11, A22, A33, A44 until ANN, because we have the same column and the same I mean that the dimensions are the same for the beams and for the rows and columns. These are the matrix elements along the diagonal from the upper left corner to the lower right corner. Okay. Another important matrix, which is the n by n identity matrix. We call it n by n identity matrix, I. Okay, so this is IN. IN means that the matrix that is having all of its elements equals to 1 across the diagonal or along the diagonal, and all the off diagonal members, they are zeros. Okay, they are zeros. Okay, so thus IN has 1 down the main diagonal and zeros everywhere else. As you can see, this is what we call it, the identity matrix 4. Why it is 4? Because it is square matrix, 4 by 4. You have 4 rows and you have 4 columns. Okay. Okay, and if A is n by m, then IN times A equals to A times IM equals to A. Take care of this, that IN, let's assume that we have A, which is n by m, okay? So we are going to multiply the identity matrix from the left, take care, from the left times A, it equals to the matrix times the identity matrix from the right, which is M here and N here. This would give us at the end the original matrix, which is A. This is what I put it here. Okay, this is what I put it here. So IN times A equals to A times IM equal to 0. Okay. Note that the dimensions must be correct. We must multiply A on the left by IN, but on the right by IM. Okay. Now let's go to the next part and take an example. So let's assume that we have A, which is, as you can see, it is 3 by 2. 3 rows, 2 columns. So we are going to multiply the identity matrix I3, the rows here, take care, I3 by A. So this is 1 0, this is the identity matrix, times by A, it equals to, you're going to find that, yes, exactly, the same matrix would result, which is A. So if you are going to multiply them, it is the same matrix will result. And if you multiply from the right, I2, why I2 here? It is the number of columns of the original matrix. If you multiply, this is A, and this is I2, the diagonal matrix, only ones here, then we're going to have, exactly, we're going to have the same matrix A, the original matrix. So take care, this is the I3 from the left, which is the number of rows, and here I2, which is from the right, identity matrix multiplied from the right. Take care, this, it should be identity matrix with the dimension of exactly the columns. Okay. And then the last thing is the matrix transpose. The matrix transpose is something easy for us. If A equals to I and J, then is an n by m matrix. The transpose of A is m by n matrix defined by A transpose A Ji. So instead of this, A transpose is going to be A, take care here, it is Ji. Okay, here it was Ij. Okay, we formed the transpose by interchanging the rows and columns of A. So let's have an example here. This is 2 by 1, 2, 3, 4. This is 2 by 4 matrix. A 2 by 4 matrix, okay, then transpose of this is going to be, each row is going to be the column here. So this column is going to be here, and this row is going to be here. That's it. This is the meaning of the transpose. Okay. Take care that there are some qualities here or characteristics that In for the identity matrix, the transpose of the identity matrix is going to be In. Okay. It is the same. The transpose of the identity matrix is going to be the same. For any matrix A transpose of the transpose, okay, the transpose of A transpose is going to be A. Okay, take care of this second property. And the third property, that if AB is defined, then AB transpose, take care of this, equals to B transpose times A transpose. Take care of this. If it's AB transpose equals to B, the second matrix, transpose, times A transpose. Take care, it does not equal to A transpose times B transpose. Take care of this, it doesn't equal that. Okay? Okay, so this is the, I think this is the end of our video. I hope that you have understood it, and I think that you can go through this video and you can understand the main operations of it. Thank you, and see you in the next video.